Okay, after we've talked about the different isomers, I would like to talk now a little bit about the reactions that we see in organic chemistry. And the important thing to realize is that organic chemistry is, most of the time actually rather easy, as long as you realize where is the charge. And the question always is, if you have a charged part, somehow that's something that is positively charged and something that is negatively charged, you get exactly what you would expect. Positive charge wants to go to the negative charge and vice versa. And this, of course, explains all the reactivity that you can see in organic chemistry. And we'll discuss that when we dive deeper into the different reactions that we discuss throughout our lecture. But of course, first of all, I would like to discuss the terms that are associated with this positive charge and this negative charge. And there are basically two different ways how you can split up a sigma bond. And you see that here, two atoms here, A and B. Of course, in our case, it's most likely carbon atoms, but could be basically any atoms. If you split this bond, because one line here corresponds now to two electrons in a homogeneous fashion, so each atom gets one electron, you call that a homolysis, and in the end you get like a radical. A radical is a fragment or an organic molecule, and basically it doesn't need to be an organic molecule, but something where you have a molecule that has an unpaired electron. And of course, if you split a sigma bond in this way, you get like two radicals, one radical A and one radical B in this case here. This happens, also very important. We'll just discuss a little bit about the reactivity of these radicals. But they are not that important in, for example, organic chemistry or in industrial chemistry. You sometimes see that, but not as often. Way more important is the second case, the so-called heterolysis, where one of the binding partners gets all the electron density that's stored in these bonds. So they get like both electrons here. And so we are left, if we assume that one partner also contributed an electron, we are left with a cation that's positively charged, and we are left with an anion that's negatively charged. And of course, they would like to meet again to form again this bond. And here we see the implementation this bond breaking has on the different orbitals. Here again, we see a tetrahedral, so an sp3 hybridized carbon atom. And here we can see if this carbon-bromine bond is broken in this homogeneous way, in this homolysis, we are getting an sp2 carbon atom where the one radical is stored here in this p orbital that's left over. So that's what I talked about in the beginning when I said that the p orbitals and the sp hybridized orbitals basically have different functionality, and the radical is now in this p electron. And of course, we also get like this bromine radical here. That's probably way more interesting for in terms of reactivity. If we look into this heterolysis case, we see two different things that can happen. First of all, for the carbocation, we see that the bromine atom now takes the whole electron pair from this sigma bond here, takes it, we get like a bromide anion, so bromide, and we are left with a carbocation, and this is again sp2 hybridized, and there's no electron in this 1p orbital, and this is of course energetically favored. So you can memorize the carbocations. They are, as long as they have like 3 bonding partners, of course, they are always sp2 hybridized. And so when the carbocation is approached by something that has electron density, it approaches either from the top or from the bottom of this, basically along this bonding partners. This is very important. And the other thing that can happen, of course, now for the carboanion, if the carbon atom takes the negative charge, for example, if like a carbon atom gets deprotonated, so a base takes up a hydrogen atom, and the carbon atom now gets like the lone pair, then we can either find an sp3 hybridized carbanion. So we have like still this tetrahedral angle, as we've seen in the beginning with ammonia. Or we can have an sp2 hybridized carbanion, where we see it's similar to the carbocation, where we have this. And this is, of course, both of them are equally good in describing basically the case around the carbon atom. And it's important to remember these hybrid orbitals is just a model to help us explain chemistry in a way. And no one can directly say, okay, this one is correct and this one is correct. But it depends a little bit on what kind of reactivity you observe, which one is basically in the actual case more relevant to explain a certain reactivity. But of course, this changes. This hybridization is very useful to explain where the electron density goes, that we can later on use for certain reactivities. And of course, these carbocations and anions and radicals, they can be stabilized. And one very important thing that can stabilize, for example, carbocations, is the so-called I effect or the inductive effect. And what is happening here is depicted here in this little sketch. Here we have a carbocation that's surrounded by 3 R groups. So this is, of course, not an atom. This is the organic, basically the organic way of representing other carbon-based moieties. And these carbon-based moieties, they now push electron density onto this carbocation. And as we've just discussed, carbocation is positively charged, but because they are pushing electron density onto the carbocation, it's more stabilized. Because a carbocation needs electron density to get stabilized, and if it gets basically force-fed somehow electron density by neighboring groups, then that's very good, and it stabilizes the carbocation overall. And of course, this effect diminishes if you remove one of the organic moieties at the carbon atom. It gets detached and replaced by a hydrogen atom. Then we get like just a secondary carbocation, and this is less stabilized and thus less stable. So this is why we see the sign here. And of course, same way, a primary carbocation is less stable than a secondary carbocation. And in the end, the methyl carbocation, where we have just 3 hydrogen atoms attached, is even less stable. So this is very unfavorable. And why is that? We have just seen the inductive effect. This is something to do with the electronegativity of the atoms. So you remember electronegativity is something that you've discussed in the introduction to chemistry. Basically describes how much electron density or how much of the electron density of a bond is located at either of the binding partners. And if the electronegativity or like the electron negativity difference is 0, then both atoms share the electron density in a very polite way, you could argue. So both of them get like the equal share. But as long as one atom is very much more electronegative, it basically pulls on this electron density in the bond and wants to take it. And that's why it's then partially negatively polarized, and then the other atom, of course, because it loses electron density, gets partially positively polarized. And in our case here for the methyl group, it's so that the carbon atom is slightly more electronegative than the hydrogen atom. So it slightly pulls a little bit on the electron density in the carbon-hydrogen bonds. And then because this carbon atom here that we are now discussing pulls on like basically 3 carbon-hydrogen bonds, 1, 2, 3, it gets a little bit more electron density. So the carbon atom is slightly negatively charged. And this slight negative charge can, of course, be used to stabilize this neighboring carbocation that, of course, also has a very it has like, if you would use like an unchemical term in a way, it has like a thirst for electron density because it needs to have the electron density to stabilize itself somehow. Another effect that you could, of course, discuss is this so-called hyperconjugation, where electron density in a neighboring carbon-hydrogen bond is basically partially transferred into this empty p orbital that we've just discussed, and this also stabilizes the effect. It's the same as you would form like a pi bond between like 2 p orbitals. Of course, it's not that strong, and it's not like an actual bond, but it's a slight way to again stabilize these atoms in a way to stabilize these carbocations. And then we can see that here move myself to the top right corner now so that you can see that. Of course, this is even better if you have like another hetero atom here. An oxygen atom is now, first of all, you would suspect that it's a little bit worse because it has a high electronegativity than a carbon atom, so it pulls electron density from our already electron diminished carbocation. So the carbocation is rather unhappy, but the oxygen atom has 2 lone pairs, so you can use this electron density of the oxygen to stabilize your carbocation in a so-called mesmeric or M effect, and this is very good. But we'll come to this even more when we discuss about the different benzene molecules, because there it plays like a very important role in how stable something is. Okay, that was it for the mesmeric effect, and then for the carbo anions, we see that here at the bottom left, there the trend is directly opposite to what we've seen for the carbocations, exactly for the same reason. If we start again with the tertiary carbo anion, we have here the effect that previously stabilized our carbocations by organic moieties pushing electron density onto our electron deficient center. This is now a very much negative effect because our carbo anion already has a lot of negative charge, so it rather wants to get rid of it somehow, and it cannot because the other groups are also pushing electron density onto it. So that's not something that we would like to see. So the tertiary carb anions are less stable. And then, of course, the methyl carb anion here in this case doesn't have the hydrogen atoms do not have a strong inductive effect. So this is the more stable. This is the most stable carb anion here. Of course, the effect changes if you change from a plus I inducing group from, for example, this carbon. From carbon-based moieties to, for example, fluorine atoms. Fluorine atoms, again, very much negative, a very strong electronegativity, so high electronegativity, so they strongly pull electron density out of their binding partners, and that's, of course, for the carb anion now very much the desired way because it has too much electron density. So the fluorine atoms just pull on the electron density and thus diminish the electron density, and thus the carb anion is stabilized. So we can summarize: carb anions are stabilized by minus inductive effects or negative inductive effects, so minus I groups, whereas carbocations, it's the other way around. They are more stabilized if we have plus I substituents because they push electron density onto the electron deficient center. The other important effect here that we have just touched is the mesmeric effect, because here we can use the electron density of neighboring atoms in so-called mesmeric structures to stabilize a carb anion or a carb cation, depending on what you're looking at. But we'll discuss that again when we talk about chapter 22, the benzene molecules.